Thanks a lot. Thank you very much for the invitation and also for the introduction. Right, I think this is my either third or fourth talk. I think one of those joint things I give 2 talks, so possibly fourth talk. But yeah, so as Roy said, I wanted to talk about prismatic cohomology in these lecture series. So this is a new cohomology theory, and I will discuss it extensively in these lectures. But my plan for the lectures is to, so in the first lecture, I will maybe try to tell you what the cohomology theory is, like what problem was it trying to solve, and give you a sampling of applications of other things that it's been useful for. And then I'll go into 2 of those applications in more depth in the next 2 lectures. So let's get started. So the motivation for this is really coming from classical Hodge theory, complex geometry. And so let me start there. So actually, maybe I should write this over here. For the rest of the talk, all of the talks, in fact, I'll fix a prime number p. And this will be relevant even in the Hodge theory part. Okay, so Hodge theory is a huge subject, but I will maybe summarize it by highlighting one important theorem in the subject. So this is due to Hodge and also de Rham. I believe this goes back to the 1930s, and the theorem is the following. So I'll continue over here. So let's say X is a compact Kähler manifold. Kähler. The thing to have in mind, at least for the purposes of this talk, is a subset of CPN that's cut out by the zero locus of a bunch of equations. So an algebraic variety, if you like, in projective space. And the fact that it's a manifold basically says that those equations are nice. Some Jacobian matrix is invertible, the shape is smooth. And so in this situation, there are multiple invariants one can attach to X that carry their own meaning, and they're related by Hodge's theorem, or rather the combination of Hodge and de Rham theorem. So let me start on the topological side. So here's the singular cohomology of X with complex coefficients. So X is just, for the purposes of defining this object, X is just a topological space. Is the usual analytic topology on X. And then singular cohomology is as is defined in the first course in algebraic topology. You look at sort of simplices mapping into your space, see how many holds the space has, and you build some abelian group that measures essentially how many n-dimensional holds the space has. So it's a topological invariant, and it's related to invariants that sort of see more of the complex structure. And so de Rham, first of all, tells us that this is also the de Rham cohomology of X. If you like the de Rham cohomology of C infinity complex valued functions on X. But I'm not going to focus that much on this, but rather Hodge's contribution to it, which is he gives a decomposition of this group into a bunch of other pieces. So it's a direct sum indexed by integers ij, where they sum up to n, and what I'm going to put here is this, I'll just call it hij of X. The precise nature of it is not so important, but roughly this is the subspace of de Rham cohomology, where if you think of elements here as given by differential forms, these are those differential forms which in local coordinates can be written in terms of I many dz's and j many dz bars. So you write it in terms of wedge products of holomorphic and anti-holomorphic local coordinate systems, and see how many of the holomorphic ones you need. And this is just a definition you can give of a filtration, and the fact that it's a decomposition is a hard theorem. So this is Hodge's theorem. So I want to highlight just some features of this isomorphism before mentioning a problem with it. So this is relating a purely topological invariant of X, something that does not see the complex structure, to something that is highly sensitive to the complex structure. And this is very useful because you can use that to you can use this isomorphism in both directions. You can use the topology of the variety to learn about its geometry, and you can learn the geometry to learn about the topology. And one can give a full course on Hodge theory indicating how this works. For my lectures, I'll just mention two applications, one in each direction. So for example, if you know that H1 on the left-hand side is 0, so for n equals 1, the left-hand side is 0. This is the case, for example, if the space is simply connected. If the fundamental group vanishes and the first cohomology group also vanishes. And then this isomorphism over here will tell you that H10 and H01 both vanish. But H01, or H10, I forget what I said for the normalization. But one of those is the subspace of global holomorphic one forms on the variety. And so what this isomorphism says is that if you have a simply connected compact Kähler manifold, there are no non-zero global holomorphic one forms on it. If you try to write down a one form on the variety, which is holomorphic, it's going to have poles somewhere. You're not going to be able to do it without introducing poles. And so that's some like geometric property of X that you learn from its topology using this isomorphism. Conversely, if you just think about the definition of these groups, there's an obvious symmetry. Hij and Hji are essentially the same. You're doing DZs and DZ bars, so complex conjugation takes one to the other. So they have the same dimension. And so therefore, if you take n to be odd, then the set of indices that show up here, they show up in sort of pairs. Hij and Hji each contribute exactly once. And so what that tells you is that the dimension of the odd singular cohomology is always even, because it's the sum of multiple copies of 2. And so that's again some very strong constraint that compact Kähler manifolds have, that the odd dimensional cohomology groups are always even dimensional. And this is not something that's easy to see directly just from the fact that, let's say, X is a compact Kähler manifold or X is embedded in CPN. It's a non-trivial constraint on the topology of such a space that Hodge theory provides. And so the list goes on and on. There are lots of applications like this of Hodge theory in understanding both the topology and the geometry of X. The starting point of these lectures is, however, a problem with this isomorphism and a proposed answer to this problem. And so the question I want to try to address in these lectures is the following. Or maybe first let me say it verbally before I write it down. So the obvious problem, if you think about this isomorphism from first principles, is I'm only seeing cohomology over here with complex coefficients. Singular cohomology, if you think back to your first course in algebraic topology, is defined with integer coefficients. There are interesting torsion cohomology classes on lots of topological spaces, and those are completely destroyed by the procedure of going to complex coefficients. So Hodge theory does not see anything about the torsion in cohomology, and we want to understand the torsion. And so the question more or less is how to understand the torsion in singular cohomology geometrically. And really, if you understand the rational story, then understanding the torsion story is more or less the same as understanding the sort of P primary part of it. And so I will just focus on the P primary part. So the singular cohomology with Z mod P coefficients, this is where the prime P enters. And so the question is how to understand this geometrically. Okay, so this is kind of the motivating question, and one answer I would like to propose and then expand on in these lectures is the following. Sorry, maybe before I go to the answer, I should tell you why you care about this. So maybe you just care about it because you care about cohomology with Z mod P coefficients. You care about torsion cohomology, which lots of people do. But there's one other reason that, for example, number theorists would care about this, which is if your X, so if your X is as in this example, so it's an algebraic variety, and the equations that define the algebraic variety actually have coefficients in the rational numbers, so there are no like pi's or e's in the equations, then it's a non-trivial theorem that this group over here has a natural continuous action of the Galois group of the rational numbers. So it's an example of what's called a Galois representation, and it's one of the most important examples of Galois representations that we have. And so we really do want to have some tools to understand the Galois representations that arise in this fashion. And if an answer to this question provides such a tool, then great. So I think for me, at least, that was one of the motivations for pursuing this question. And then the answer that I would like to propose in some partial generality. So this is for x nice. Well, I guess I'm assuming x is nice here. So, well, no, sorry, right. This answer is for x smooth projective. So I'm not going to be able to tell you anything about compact Taylor manifolds that are not algebraic. For non-algebraic ones, the theory is kind of, I don't know, it's beyond my pay grade. But for smooth projective varieties, so things coming from algebra, there is a proposed answer, which is the following. So it says in the geometry, or really in the differential geometry, again, just like in Hodge theory, but not of x, but rather its characteristic P counterpart. So in the differential geometry of x mod P. And I'll make sense of what I mean by x mod P in a few minutes, but roughly the idea is that if your x is defined by algebraic equations, you can take those equations and you can just reduce the equations mod P. You get a system of equations over Z mod P. You can study its solution set. And in the differential geometry of that solution set, we are going to find a differential form which will correspond to some interesting classes over here. So that's the direction in which you're headed. Okay, so that was my motivation for what we're doing and why one might care about it. Are there any questions? Okay, so let me now try to make this slightly more precise. So it's about Hodge theory mod P. Okay, and so this is where we meet the P-adic numbers for the first time. So here's the setup. ZP is going to be the notation for the ring of P-adic integers. And if you're not familiar with this or don't remember what it was anymore, feel free to just pretend this is the integers. The fact that it's ZP is just some technical improvement to this. What I'm going to say, what I'm saying is already interesting when this is just the ring of integers itself. And so what structure does this have? This is a nice ring. It's a principal ideal domain. And it sort of is some kind of a algebraic object that relates characteristic 0 with characteristic P. So there are two things you can do to it. You can invert the prime number P, and what you get is called QP, the field of P-adic numbers. This is the P-adic analog of the real numbers. It can be defined directly by saying you start with the rational numbers. On the rational numbers, there's a metric called the P-adic metric, which is essentially measuring how close to two integers are close in the P-adic metric if their difference is highly divisible by P. So P squared is closer to 0 than P is, and P to the fourth is even closer. And so that defines a metric on Q, and then if you complete, you get QP, which can also be obtained this way algebraically. So this is the analog of the real numbers. The analog of the complex numbers would be QP bar, would be the first attempt. But unlike the real numbers, this extension is an infinite degree extension. So the complex numbers have degree 2 over the real numbers. And so if you have a 2-dimensional vector space over a complete field, it's complete. But if you have an infinite dimensional vector space over a complete field, it's no longer complete. So you have to complete it. And that's going to be what I'm calling C. This is the P-adic complex numbers. And again, you might be worried that after you complete it, it was no longer algebraically closed. So you have to keep doing it over and over again. You don't have to. It's all good. So this is the characteristic 0 object that we're going to be interested in. this is a field, and as an abstract field, it's isomorphic to the complex numbers. So it's really just another name for the usual complex numbers, but now obtained through this P-adic procedure. But you can also go mod P. So you can kill P in this ring, and what you get is Z mod P. So call that P. And so this is the sense in which ZP is going to relate this characteristic zero field, which is the copy of the complex numbers, to this finite field FP. And so we're going to use this to try and make sense of this phrase over here, X mod P. Okay, so that's first object, and then the second object is X. So X over ZP is a smooth projective variety. And so what this means is defined as a zero locus of a bunch of equations in projective space where the coefficients now come from ZP, and smoothness again is some kind of a non-degeneracy condition. So let me draw a picture for what's going on. This is the kind of picture that arithmetic geometers like drawing, and I don't know how convincing it is, but I will try. So here's X, here's ZP, and really I'm drawing a spectrum of ZP, so I'll write it as so. And you're supposed to think of this as some kind of a curve, which is why it looks like that. It's a curve which has two interesting points. And the points correspond to the two fields I've drawn over here. So here's C and here's FP. And actually this curve only has 2 points, so it's a little wonky, but that's what we have. And then this X, the sort of role X plays is that it allows us to sort of define two geometric objects. Here's XC, and here's XFP. So what I'm doing is I'm just taking the equations that define my variety X, the equations of coefficients in ZP, so I can regard them as equations with coefficients in the complex numbers and look at the solutions there. That's what XC is. And I can do the exact same thing over here. I can regard the equations as having solutions over FP and then look at the solution sets there. So that's XFP. The assumptions tell me that both of these are nice geometric objects. This is